My name is Jian Zhang from Jiangsu University of Science and Technology. My presentation title is Buckling of Externally Pressurized Helically Wound Composite Cylinders. The presentation contents include the following: background, experimental analysis, analytical analysis, numerical analysis, and conclusions. First, about background. Cylindrical shells have long attracted research attention because of its excellent space utilization, satisfactory load capacity, mature design theory, and ease of manufacture. They are widely used in pressure vessels and pipelines within offshore structures such as offshore infrastructure, underwater vehicles, and subsea facilities. Composite materials are widely used in cylinder shells because of their high specific strength and stiffness, excellent energy absorption ability, and corrosion resistance. However, composite cylinders are prone to buckling, which is strongly affected by the fabrication process, material properties, and fiber fraction and arrangement. The buckling of composite cylinders have been extensively exploited using numerical, experimental, and analytical approaches. The first one is most powerful. The second one, experimental studies, have been devoted to composite cylinders because the continuous strength offering reinforcement can be oriented in any direction. Finally, the analytical approach is the most common tool for evaluating the collapse strength of composite cylinders. However, little attention has been paid to the buckling of helically wound composite cylinders in three directions. Few studies have focused on the post-buckling behavior of such cylinders. Therefore, in this study, an experimental, analytical, and numerical study of composite cylinders has been conducted. This is a methodology of the experimental analysis. According to the schematic of composite cylinders with steel flange, we carry out the fabrication of three specimens. This is a physical picture of three specimens, mainly including cleaning the steel mandrel and applying a release agent, then helical winding, removing the end bones and separating, and finally cutting and grinding. The experimental methodology include thickness measurement, optically scanning, and hydrostatic test. The fabricated samples present uniform thickness distribution, good fabricating accuracy. The longer the length of the fabricated samples, the smaller the collapse value. This is the failure picture of three specimens. Most failure began from the center of specimen. The actual crack expanded from middle to both ends. Besides, the proportion of length of outer axial crack decreases with an increase in length of composite cylinder. Failure only occurred on the side of specimen subject to hydrostatic test, which agrees with previous test results, and then the proportion of maximum width of the circumferential crack decreases with an increase in the length. And then we use analytical formula to evaluate the collapse strength of three fabricated specimens, including NASA formula AF ME formula, choice formula, chance formula. This is analytical resource. The trends in predicted collapse strengths demonstrated an identical monotonic decrease with increasing length to radius ratio. Based on the results that was obtained, the first three formulas seem to provide a marginally conservative estimation, whereas ASME code provides the most conservative estimation. The conventional analysis of mesh size obtained through eigenvalue analysis. Consequently, a global mesh size of 5 mm was selected. The mesh size number of elements nodes of 3 FE models are listed in the tables. Also, the picture in the left side is the finite element model established using commercial software Abacus. The failure initiation was calculated using Hashing failure criteria, which is based on stress expressions. For each failure mode, the fracture energy corresponds to the area of triangle OAB. The values for various modes depend on the fracture energy. The linear buckling loads of fabricated specimens do not accurately predict the test collapse modes compared with nonlinear buckling. The post-buckling appear as local dimples. The numerical post-buckling loads were identical to experimental observations. The Hashing's damage initiation criteria of less or less than 1. It is indicated that the structural damage did not occur before critical buckling in the fabricated specimens. Fiber compression was more dominant than fiber traction because of external pressure conditions. As can be seen, there's a good agreement between numerical and experimental observations. The trend in the test collapse load were consistent with numerical predictions. Moreover, as the length to radius ratio increased, the buckling load initially decreased rapidly and decreased gradually thereafter. This trend was reasonably consistent with analytical results. The trends in buckling load for each length are a monotonic increase with increasing thickness. The linear buckling load was slightly larger than nonlinear buckling load, and the difference between linear and nonlinear buckling load decreased with thickness. Finally, conclusions. The thickness geometrical measurement results of 3 specimens exhibited suitable repeatability and fabrication accuracy. The tested collapse modes of specimens were identical. Major failure occurred from center of specimen, and the axial crack extended from middle to both ends, which is typical failure mode of thin composite cylinders subject to external pressure. The collapse strengths obtained using NASA formula were closer to the tested collapse load for CY1 sample. The collapse strengths obtained using Joe's formula were close to tested collapse loads for the remaining 2. A determination of which model works best for this particular study cannot be made, since they can be a random deviation from experimental study. With that said, based on the results that was obtained, the empirical formula seemed to be valid for mid-long cylinders. The linear bucking load was slightly larger than nonlinear bucking load, which were calculated by considering geometrical nonlinearity. This finding suggested that nonlinear buckling analysis provided marginally conservative estimations. The minimum difference between the numerical and experimental model was 2.4, 12.5, and 8.9% for CY1, CY2, and CY3 specimens respectively. This confirms that the numerical results were closer to experimental results than analytical results were. These are the recent publications of my research team about composite cylinders. That's all. Thank you.